Let's finish up 2.5, the Celo theorems. Last video maybe ended a little abruptly. And let's pick up right where we left off, though, with the first Celo theorem. Theorem 2.5.7, the first Celo theorem, the reference is given in the notes for the corresponding result in the Fraley book, says, let G be a group of order P to the n m, where n is greater than or equal to 1, P is prime, P and M are relatively prime. In other words, any divisor P of the order of the group is included in this P to the n term. So there's no divisors of M, of P doesn't divide M in particular. Then the claim is G contains a subgroup of order P to the I for each I between 1 and n, and every subgroup of G of order P to the I, where I is strictly less than n, is normal in some subgroup of order P to the I plus 1. So any finite group for a given prime divisor has a bunch of subgroups of those prime order. In particular, when n equals 1, this says a lot less, but it reduces down to Cauchy's theorem. So certainly the first Celo theorem is a generalization of Cauchy's theorem. Okay, let's look at a proof of that. All this talk of I and I plus 1, it's not surprising. We'll give an inductive proof of this. Okay, so first claim, contains a subgroup of order P to the I. Second claim, a claim about subgroups of order P to the I plus 1 and some normality there. Okay. First, P divides the order of the group. N is greater than or equal to 1, so P is a divisor of the order of the group. So G contains an element, let's denote it A, and therefore a subgroup generated by A of order P. So says Cauchy's theorem, so element A is of order P, and the group it generates is of order P. I told you, think of Cauchy's theorem as claiming the existence of subgroups of certain orders. That fits in better with the current conversation in the Celo theorem setting. So we have the result shown in the existence of a subgroup part for I equals 1. Following from Cauchy's theorem, so that'll act as the base case, and we'll do an inductive argument to show the existence of the other subgroups, and then we'll take care of the normality condition. So we perform induction on index I, assume G has a subgroup H of order P to the I, where I is between 1 and n, not equal to n, need a little room to squeeze a new subgroup in there. Each of these, of course, then are P subgroups of G, so in the corollary that we just saw based on their orders. And now we're going to construct a group H1 of order P to the I plus 1, where H1 is a subgroup of G, and that'll take care of the existence part, and H is a normal subgroup of H sub 1. And that'll take care of the second claim, the claim about normality. Okay. So we're assuming G has a subgroup of order P to the I. That's the induction hypothesis. And we'll construct the group of order P to the I plus 1 and then establish the normality, and that'll do it. Okay, if we look at the index of H in G, the number of cosets of H in G, that's the order of H divided by the order of G. Lagrange's theorem says everything's finite, so no concerns over division. So I can interpret Lagrange's theorem in terms of quotients of numbers. And group H is of order P to the I, where I is strictly less than n. Yet group G has an order that's divisible by P to the n. So when you perform this division, there's still a factor of P left in the quotient. The order of H is less than or equal to P to the n minus 1, so still an extra factor of P left, and we can draw the conclusion that P divides that index, the index of H and G. First off, next, let's look at the normalizer of H and G. For the record, that's all lowercase g and big group capital G, such that conjugation G, H, G inverse yields H itself. Notes talk right here of group action, though we certainly haven't seen the last of group action, but simply the definition of the normalizer. So H is a normal subgroup of the normalizer, of course, right? Look at the definition of normal subgroup, if you like. I guess that's part 5, Theorem 1.5.1. We had a whole bunch of conditions that we took to be the equivalent conditions that we took to be the definition of a normal subgroup. But, I mean, of course, H is a normal subgroup of its normalizer. That's why that thing's called a normalizer. Corollary 2.5.6 tells us that the normalizer of H doesn't equal H. Let's run back and take a peek at that. It's in the previous video, but 2.5.6 said, if H is a P subgroup of a finite group G, which is what we have, such that P divides the index of H and G, then the normalizer of H and G does not equal H. In other words, there's more stuff in the normalizer than just the elements of H. Of course, all the elements of H are in the normalizer. P dividing the index tells you there's more stuff in the normalizer, and that's what we're using here. So the normalizer of H and G doesn't equal G because P divides the index of H and G. That was exactly the hypothesis of that corollary. So we can use this conclusion of non-equality. So if we look at the cardinality of the quotient group, normalizer of H, mod H itself, that's a group of cosets of H in the normalizer. We count those using this index notation. The index of H in the normalizer of H is the number of cosets of H and G. Those are the elements of this quotient group. Since the normalizer of H and H itself are different, then that index is greater than 1. If we only get indices to equal 1 when we have equality of the group in the subgroup. So by lemma 2.5.5, which states, we'll take a quick look at that as well, states that the index here is congruent to the index here, mod P. So something we did in this setting of P groups. Let's look at that. All right, if H is a P subgroup of a finite group G, then the normalizer, the index of H in the normalizer of H is congruent, mod P, to the index of H in G. Bad place for a new line, but that's exactly what we're looking at. And the claim is those two are congruent, mod P. Back to the proof. Okay, so right here is that congruence, mod P, some other stuff being said as well. We just saw 1 is strictly less than this index, which equals the order of that group. 1 strictly less than order of that group, which equals the index. This index is congruent to that index, mod P, and this index of H and G, is 0 mod P, because we said right there, P divides the index of H and G. P divides it, and that quantity is 0 mod P. So that gets us to this stage. It's this quotient group we want to look at. This quotient group is 0 mod P, and it's not zero itself, strictly greater than 1. So P divides the order of that quotient group. So here we have a group, and P is a prime divisor of the order of that group. Not surprisingly, Cauchy's theorem is going to arise in this setting. Remember, what we're looking for is a subgroup of group G of order P to the I plus 1. Okay, we've wandered off and now we're talking about normalizers and quotient groups and related to the normalizer. So we'll have to get back to where we started. But anyhow, for this group, this quotient group, normalizer of normalizer of H and G mod H, since P divides the order of that group, then that group must have an element and hence a subgroup of order P. That's what Cauchy's theorem says. Now, elements of the quotient group would be, say, left cosets of H. So there's some element, let's call it BH, a left coset of capital H, and the subgroup which it generates must be of order P. So we found a group of order P in some quotient group. We got to get back to the conversation about group G first off, instead of this quotient group stuff. Well, corollary 1.5.12, we'll look at that, tells you what this group of order P looks like. Okay, we've got, let's see, the normalizer of H and G, that's some subgroup of group G. So we want to look at this quotient group, mod H, and sort of describe it in terms of a quotient group, mod H, as it relates to a different subgroup of group G. And that's where we're going to get a group H sub 1, and that'll be the group of order P to the I plus 1. But let's look at corollary 1.5.12. 1.5.12, just happen to have it in the background, says this. So it's been a while since we've looked at this stuff, but it says if N is a normal subgroup of a group G, so we can talk about G mod N, then every subgroup of G mod N is of the form K mod N, where K is a subgroup of G that contains N. And there's some furthermore stuff that we don't need for the current conversation. So if we've got a subgroup of this quotient group, then it must be of a particular form. That is, it's K mod N, where K is some subgroup of G that contains that normal subgroup N. If N is normal in G, then it's normal in any subgroup of G. So we do have a normality claim there, and it does make sense to talk about that quotient group. Back to the proof. Well, that's what we have. We have a subgroup of this quotient group of order P. Okay, well then that means this subgroup, the group generated by element BH, that left coset, that subgroup of the quotient group, which is of order P, must be of the form H1 mod H, where H1 is some subgroup of the normalizer and H1 contains H. That's exactly what corollary 1.5.12 said. This is what subgroups of a quotient group look like. And here's I leave it to you, here's a little details to make the notation here align with the symbols that were used in the corollary. So here's a quotient group, H1 mod H. We know H is normal in the normalizer. H1 is a subgroup of the normalizer. H1 is a subgroup of the normalizer. So H is normal in H1 as well, by the way. So we could look at orders. And the good thing about H1, see if I can find it, it doesn't explicitly say here, it's implied here. H1 is a subgroup of group G. It's a subgroup of the normalizer of H and G, and then that's itself is a subgroup of group G. But H1 that's the group we're looking for, it turns out. H is normal in H1. That's why we looked at the normalizer. Remember what we're trying to do. We're trying to show the existence of a group of order P to the I plus 1, the induction step, that is of order, a group of order P to the I plus 1. That's the existence part in the induction step. And We started this with group H of order P to the I. We need it to be normal in that group. And we got the normality. As long as H1 is the correct size, we got the proof. And the proof on the size, thanks to the fact that we've got Lagrange's theorem and finite groups everywhere. The cardinality of H1 is the cardinality of H times the cardinality of this quotient group. If you like, Lagrange's theorem says I can write the cardinality of this quotient group is the quotient of the cardinalities. Cardinality of H1 divided by the cardinality of H, and the cardinalities of H cancel. That's how you get the equality there. But H, by hypothesis, was a group of order P to the I, was the induction hypothesis. And H1 mod H, that's this, a representation of this group generated by this left coset that is a group of order P, thanks to Cauchy's theorem. In other words, the cardinality of H1 mod H is P. That one came from Cauchy's theorem. Picks up a factor of P right here. And multiplying, we get P to the I plus 1. That's the group we were looking for. It needed to be of order P to the I plus 1. Now the result follows by induction. And it needed to have this group of order P to the I, group H, as a normal subgroup. And it does. So by induction, the result holds for all appropriate I. This is a finite setting, all I between 1 and n inclusive. H is a normal subgroup of H1, and H1 is the right size, and that's what we needed to show. Back to the notes. And some terminology. Subgroup P of a group G is said to be a Celo P subgroup, P is prime, if capital P is a maximal P subgroup of G. That is, if we have another subgroup, another P subgroup, H between capital P and group G, then P and H must be the same, maximal in a set inclusion sense, if you like. So we've defined both P subgroup. A P subgroup was a subgroup in which all the elements are of order P. A P group was a group in which all the elements were of orders, power of a prime P, I should say. So P subgroup, all elements are of order power of prime P. Celo P subgroup is maximal, a maximal P subgroup. Wouldn't be surprised if, when we're in a setting like this, I bet those Celo P subgroups are the ones of order P to the n. They are. We'll put together a little argument for that. So no surprise, the first Cielo theorem implies with the order of G as P to the n m, every finite group has a non-trivial Celo P subgroup. It would be the group of order P to the n, as we're about to show. And that's proved to exist by the first Cielo theorem. More specifically, it's a little corollary. Let G be a group of order P to the n m, P prime, n greater than or equal to 1, P and m relatively prime, as discussed earlier, coprime sometimes it's called. Let H be a P subgroup of G. And we have the following claims. H is a Celo P subgroup of G if and only if the order of H is P to the n. Not surprising that it would be a maximal P subgroup and hence a Celo P subgroup. Second claim, every conjugate of a Celo P subgroup is a Celo P subgroup. Maybe not intuitive there. Thirdly, if there is only one Celo P subgroup, capital P, then capital P is normal in G. Not a surprising result once part 2 is established. Let's look at a proof of those three claims. Okay, claim 1, H is a Celo P subgroup if and only if the order of H equals P to the n. Not surprising. H is a P subgroup if and only if the order of H is some power of P. We established that in a corollary earlier. The first Cielo theorem tells us, hey, if the order of H is P to the I, where that exponent is less than n, there's a bigger there's a bigger P subgroup that contains subgroup H, and so subgroup H isn't maximal. So subgroup H isn't a Celo P subgroup. So we must have P to the I for some I. If that I is strictly less than n, you don't have a maximal P subgroup. So you don't have a Celo P subgroup. So the only candidates for Celo P subgroupness are those subgroups of order P to the n. The subgroups of order P to the n will be maximal P subgroups. That is, they'll be Celo P subgroups. So not much of a surprise on that one. Proof of the second one, we're actually going to rely on an old exercise trying to show, next slide, every conjugate of a Celo P subgroup is a Celo P subgroup. Conjugation preserves a collection of Celo P subgroups. Could describe it in terms of group actions, of course. Exercise 1.5.6 tells us if you conjugate a group, you produce a group that's isomorphic to the original group. So if I take a Celo P subgroup and I conjugate it by some element, that will produce another group of the same order. We only had a Celo P subgroup if it was order P to the n. Part 1 says, well, when you take a conjugate, you get a group isomorphic to the given group. So anyhow, it'll be of order P to the n as well. And so part 1, it'll be a Celo P subgroup also. Thirdly, if there's only one Celo P subgroup, capital P, then capital P is normal in the group. So normal subgroups as of late have been discussed a lot in terms of conjugation. And that's why we introduce conjugation as a group action. Well, what if you conjugate this subgroup P? Well, you'll get another Celo P subgroup. If capital P is a Celo P subgroup, so is its conjugate. That's what part 2 says. But there ain't but one. Okay, you conjugate it, it must give capital P back. If there's only one Celo P subgroup, capital P, we know that by part 2. If you conjugate it, that's got to give you a Celo P subgroup back. There's only one, so that conjugation must yield the original Celo P subgroup. GP G inverse equals P. No matter what the conjugation was, this must hold for all G, lowercase g, and group capital G. And that's exactly one of the conditions that tells you that P is a normal subgroup. So only one Celo P subgroup implies that Celo P subgroup is a normal subgroup of the group G. Okay, so part 1 allows us to discuss Celo P subgroups entirely in terms of their order. We were able to describe P subgroups entirely in terms of their order as well, a bit earlier. Second Celo theorem says, let's draw a picture for this one. This is so rare I can draw pictures in algebra. Says if H is a P subgroup of a finite group G and capital P is any Celo P subgroup of G, then there exists X and G such that H is a subgroup of X, capital P, X inverse, the conjugation of the Celo P subgroup by that element X. In particular, any two Celo P subgroups are conjugate. That's a little something new. Think of it like this. Here's Celo P subgroup capital P. Here's P subgroup capital H. So capital H is a P subgroup. That's all tied into this powers of the prime stuff. P is a maximal Celo, a maximal P subgroup. That is a Celo P subgroup. Well, H and capital P must share something. They got to share the identity. Maybe they share some other stuff too, but they certainly share the identity. Think of this as a situation where capital H and capital P don't share everything. Capital H is not a subgraph of a subgroup of capital P. Then we can conjugate this green Celo P subgroup, capital P, by some element X to produce a new Celo P subgroup that will contain subgroup H. So I don't know, envision it as some kind of rotation or something like that, if you like, but a tiny little visual to give a touch more meaning to this. And let's look at the proof. Okay, H is a P subgroup, finite group G. Capital P is any Celo P subgroup. Okay, for the first time today in this video, let's look at some group action. Let S be the set of all left cosets of capital P and G, and let H, the P subgroup, act on this set S by left translation. Set S sub 0, as always, is defined as the elements of set S, in this case, left cosets of P, such that the group action leaves those things fixed as we range over all elements of the group doing the action, in this case, group H. Exact same thing we had in the past. So maybe the first time I didn't put my stars in there to indicate the group action, but this is exactly what we had before. The group action is left translation. H acts on this left coset to produce the same left coset. S sub 0 was all elements of the set that had orbits of cardinality 1 was the notation we had used for the S sub 0. We knew lemma 2.5.1, we proved that the cardinality of S and the cardinality of S sub 0 were congruent mod P in such settings. So I won't look that one up. That's exactly what lemma 2.5.1 said. Hey, here set S is a set of all left cosets of P and G. How many left cosets of P and G are there? Well, that's what the index represents. It'd be the index of P and G, because the index represents the number of, say, left cosets in G and right cosets in G. Don't make me go back to chapter 1. Yeah, the number of left cosets equals the number of right cosets. Excuse me, the cardinality of the set of left cosets equals the cardinality of the set of right cosets. Everything's finite in this section, though. So the index of P and G is also congruent to the cardinality of S sub 0 mod P. But P doesn't divide the index of capital P in G. Hey, the index of capital P in G is the cardinality of G divided by the cardinality of P. I need Lagrange's theorem there. Yeah, I think I can cover that with Lagrange's theorem. Nobody said P was a normal subgroup necessarily. So we're not talking quotient groups. We're counting cosets. But still, Lagrange's theorem applies to that. And capital P, it's a Celo P subgroup. So if capital G has order P to the n times m, capital P has order P to the m, P to the n. All the factors of P are canceled out in this quotient, and you're only left with something, call it m, which is relatively prime to P. So P doesn't divide this quotient, P doesn't divide this index, and that's what we've said here. P doesn't divide the index. Okay, so that index is not 0 mod P. All right then, that little set S sub 0 does not have a cardinality that's 0 mod P. In particular, that cardinality is not 0. So set S sub 0 is non-empty. It has a cardinality of at least 1. There exists something in it. The things in it are left cosets of capital P. So there's some, say, XP. Left coset of Celo P subgroup, capital P, that's in S sub 0. All right, a string of equivalences, if and only ifs. This left coset is in S sub 0. If and only if definition of S sub 0. When we act by left translation on that coset, we always get that left coset out. And that holds for all, there's a little typo here, all H in group capital H, regardless of what H is, then we get that left coset fixed. So I'll get that typo fixed in the notes. It should read lowercase h, not lowercase x. So when the group acts, it simply leaves that left coset as is. This occurs if and only if we get x inverse hx, p equal to p, interpreted as multiplying on the left by x inverse, the set equality. So we've dealt with the set equalities. So we get these two sets equal if and only if these two sets are equal. Again, for all H, got to correct here, all H in group capital H. We get a left coset of P equal to P itself, if and only if that thing that we've multiplied on the left of P to be an element of P. So we need this to hold if and only if x inverse hx is in P. That holds for all elements of subgroup capital H, or in other words, x inverse capital Hx is a subgroup of P. So we've taken a step from talking about elements being in P to a whole set of elements being in P. And this occurs if and only if, think about, sort of some kind of cross multiplication type deal. H is a subgroup of x, P, x inverse. And that's what we were trying to show. We were trying to show H is contained in some conjugate of P. There's the conjugate. Where'd the x come from? The fact that S sub 0 was non-empty. We knew there was something in S sub 0. That's where the x came from, ultimately. So that's how the conjugation is performed. So we've got H contained in that conjugate. Second claim, any two Celo P subgroups of G are conjugate. All right, simply take H to be a Celo P subgroup. Then it'd have to have the same cardinality as P. It'd have to be, lowercase p to the n in the way we've used the notation. I know cardinalities of Celo P subgroups now. When we do the conjugation, the cardinality of P equals the cardinality of a conjugate. We know conjugates of Celo P subgroups are again Celo P subgroups. So both of these have to have the same cardinality, p to the n, as described above. So we can draw the conclusion that the cardinality of H is the cardinality of that conjugate. That's right, transitivity from here to here. And it must be then that H equals xp x inverse. They got the same size. And remember, we showed upstairs, H is a subgroup of xp x inverse. It's a subset of the same cardinality, and everything's finite. So that yields an equality of the two sets. And that justifies the second claim. So H was an arbitrary Celo P subgroup. It is a conjugate of the given Celo P subgroup, capital P. Back to the notes. Okay, we got two more results, and then we'll illustrate this stuff with some relatively simple examples. Following two results state the third Celo theorem and then something about normalizers. So let's go through both of those, neither one terribly long. Third Celo theorem, as we'll show, so with some applications, is useful. What this does is this counts the number of Celo P subgroups. If G is a finite group and P is a prime, then the number of Celo P subgroups of G divides the order of G and is of the form Kp plus 1 for some k greater than or equal to 0. Not sure why they chose to express it quite like this. Another way of saying that is the number of Celo P subgroups divides G and is 1 mod P. So we got a multiple of P that they've introduced here with this parameter K. Okay. Second Celo theorem tells you any two Celo P subgroups are conjugate. So if capital P is a Celo P subgroup, the number of conjugates of P is the number of Celo P subgroups. I know they're conjugate to each other, so if I can count the number of conjugates of a given Celo P subgroup, that'll tell me the total number of Celo P subgroups. We need a result from section 2.4 dealing with the group action. We're about to claim that the number of conjugates of P and G is the index of the normalizer of P and G in G, and that this divides the order of the group. Let's run a look at the notes, looking for corollary 2.4.4. I should have that in the background as well. 2.4.4, part 3. The number of subgroups of G conjugate to K. Setting here was G is a finite group and K is a subgroup. Number of subgroups of G conjugate to K is the index of the normalizer of K and G in G, and the claim also that this divides the order of the group. So there's your divides the order of the group. Same thing we have, except we're not looking at a subgroup K. We called it P. It was a Celo P subgroup. So the index will tell you the number of conjugates and is a divisor. All that comes from this one corollary. So corollary 2.4.4 part 3 tells you the number of conjugates is the normalizer in G of that subgroup and is a divisor. Okay, so we got the divisor part. We still need to do the little counting thing and get the 1 mod P part. Normalizers, eh? Well, let S be the set of all Celo P subgroups of G, and let P act on S by conjugation. All right, we're interested in, S is a set of all Celo P subgroups. We're interested in the number of Celo P subgroups. We're interested in the cardinality of S. We related the cardinality of S to the cardinality of S sub 0 in our previous stuff. So let's talk about S sub 0. They were the same mod P as what we had by an earlier lemma from this section. So let S be the set of all Celo P subgroups of G. The cardinality of that's what we're interested in. And let P act on this set by conjugation. S sub 0 then would be all elements of set S, that is all Celo P subgroups in G, such that that conjugation by an element of P fixes that Celo P subgroup for all elements of P. So if Q is in S sub 0, we're going to show it equals P, it turns out. If Q is in S sub 0, then XQ, X inverse, equals X for all X in Celo P subgroup capital P. This is the group action, it's conjugation. We have such a Q if and only if P is a subgroup of the normalizer of Q in G. Concentrate on this part right here. This says XQ, X inverse equals Q for all X in P. What's the normalizer? Well, that's all X in G such that XQ, X inverse equals Q. Well, if Q is in S sub 0, then it satisfies this condition for all X in P. That's some of the X's in G. So we can draw the conclusion that Celo P subgroup capital P is a subgroup of the normalizer of Q in G, assuming Q is in this set S sub 0. So both P and Q, nobody said these were distinct. Turns out they're the same, as we'll see. But both P and Q are Celo P subgroups of G. They're conjugates. Let's see, I don't want to deal with this. P was given as a Celo P subgroup, and Q was chosen from the set of Celo P subgroups. That's how I want to deal with it. So both of these are Celo P subgroups of G. And so they're subgroups of the normalizer of Q and G, as we just saw. And so they must be conjugates. They're Celo P subgroups in both G and also in this subgroup. This subgroup contains P and certainly contains Q. So P and Q are also Celo P subgroups of this group, normalizer of Q and G. Hey, any two subgroups, any two Celo P subgroups in a group, be it G or this normalizer, they're conjugates of each other, as we showed earlier. So P and Q must be conjugates of each other in this normalizer. Q's normal in the normalizer. That's why the normalizer is called a normalizer. So if you conjugate Q in the normalizer, you're just going to get Q back. It's the normalizer. You conjugate Q with something in the normalizer, it produces Q. So when we take a conjugate of Q, and we should be able to get P by conjugating Q, as we saw earlier, P is a conjugate of Q in the normalizer, but when you conjugate Q, you simply get Q back. Well, then P must equal Q. So it's an argument put together through conjugation and the fact that we're dealing with Celo P subgroups of the normalizer of Q and G. P and Q are the same. S sub 0 was the set of all Q that were fixed under conjugation. We took an arbitrary element of that set and found out that we must have nothing but subgroup P. S sub 0 consists only of that Celo P subgroup, capital P. So the cardinality of S sub 0 is 1. Now we can use lemma 2.5.1 from earlier in this section that told us the cardinality of S was congruent to the cardinality of S sub 0 mod P. We just saw S sub 0 only contains one thing, so the cardinality of S sub 0 is 1. And so the cardinality of S is 1. Mod P is a conclusion. That is, the cardinality of S is of the form Kp plus 1 for some K. And S was, what was it? The set of all Celo P subgroups. So the number of Celo P subgroups is of this form. We had the divide order of the group on the previous slide. Now we've got it of the proper form. This will allow us to put together some counting arguments, as we'll see in some examples. But one last claim. If P is a Celo P subgroup of a finite group G, then the normalizer of P and G equals, okay, this one is a bit more of a mouthful, the normalizer of P and G in G. We'll give this a name and have a briefer way to describe this here in the body of the proof. But awkward verbiage, symbolically, there's the claim. Okay, so we start with a Celo P subgroup, and then we're looking at a normalizer of that, and then a normalizer of the result of that. And the claim is the second application of finding normalizers doesn't change anything. You know, a conjugate of a Celo P subgroup is a Celo P subgroup. Second Celo theorem told us that. So conjugate of P, given that P is a Celo P subgroup, conjugate of P is a Celo P subgroup of any subgroup of G that contains that group P. If we have a Celo P subgroup, I know the order of it. If it's also a subgroup of a subgroup of G, that's a subgroup of group G, then P is also a Celo P subgroup of that subgroup. So this is where I could use to write some stuff out linearly. But we base that argument entirely on order. I know the order of P. It's P to the n, you know, with the usual notation we had about orders of groups. And I can tie together Celo P subgroups to their orders. That's what the corollary allowed us to do. P is normal in the normalizer of P and G. like I said, let's just call that capital N to at least make the verbal description a little bit simpler. So let capital N denote the normalizer of P and G. Of course, P is normal in its normalizer. That's why it's called a normalizer. One more time for the record. It's all the X and G such that X, P, X inverse equals P itself. Then P is the only Celo P subgroup of capital N by the second Celo theorem. Remember, the second Celo theorem told you any two P subgroups of, say, group N must be conjugates of each other. But when you conjugate P in the normalizer, nothing happens. Conjugate P in the normalizer of P, you just get P back out. So P must be the only Celo P subgroup of capital N. Conjugation doesn't change it because you're conjugating by things in the normalizer of P. So if we choose X in the normalizer of N in G, this occurs, X is in this normalizer if and only if X capital N, X inverse equals capital N. Definition of normalizer. You take the group, conjugate it by X, and you get the group back. It's the same thing we had up here when we looked at the normalizer of P. Now we're looking at the normalizer of N. Same idea. P was a Celo P subgroup up there. Down here, capital N is a, I don't know, something else. But it's just a definition of normalizer. So we get X in this normalizer if and only if this occurs, definition of normalizer. This implies X, P, X inverse is a subgroup of N because P itself is a subgroup of N. Let's see. N, here's N, up here. If I take an element of P and conjugate capital P by that element, of course I get P back out. Conjugation by an element of the given group, it's actually an inner automorphism. It's an example of an inner automorphism to show off some lingo from earlier. But you take an element of P, and of course we get this type of equality. So P itself is a subgroup of this normalizer. P is a subgroup of N. Now you might say, hey, let's take this and conjugate both sides by X, multiply on the left by X and the right by X inverse. What do you get over here? X, P, X inverse. Ta-da. Over here you get X in X inverse, but that equals N. And that's how I can justify this equation. So X, P, X inverse, we've got that to be a subgroup of capital N. This must be then, this conjugation must be a Celo P subgroup of N, because when you conjugate this group, you get a group of the same order, putting together an argument that Celo P subgroups are always order P to the N, where we've used those P to the N symbols as previously. I can describe Celo P subgroups or recognize them by their orders, as that was the benefit of that corollary. Since capital P is the only Celo P subgroup of N, let's see, P is the only Celo P subgroup of N. We're almost there. Because it's the normalizer, capital N equals, there we go, it's the normalizer of P. So any conjugation simply reproduces P. Yeah, P is the only Celo P subgroup of the normalizer. I know two Celo P subgroups are conjugates. Conjugation doesn't change in this setting. P equals X, P, X inverse. So we started with X is in this normalizer. We've deduced P equals X, P, X inverse. All right, that means X is in this normalizer, the normalizer of P and G, that is X is in itself. So we've shown an arbitrary element of this thing is also an element of the regular old normalizer. That is, this thing, normalizer of the normalizer, is a subset of the normalizer of P and G. All right, trying to show equality, of those two groups. We've got the subset inclusion. We actually got the hard half of the subset inclusion. We just need to reverse that, and then we've got equality. Clearly, the normalizers of any subgroup of G contain all the elements of that subgroup. Yeah, the normalizer of P and G certainly includes all the elements of P. So if X is an element of the normalizer of P and G, then X is certainly an element of the normalizer of that group in G. We took an arbitrary element of this and showed it's in that. That is, we've shown this subset inclusion. That reverses what we had on the previous slide. And there's your subset equality. And of course, normalizers are groups. We showed that way back when. So these two groups are equal. Back to the notes and some illustrations of the Celo theorems. Back to the notes in this section. Okay. All right, an example from Fraley, pretty easy little example to illustrate the existence of Celo P subgroups, and we'll count them. And we'll look at conjugates of them, and that'll illustrate all three Celo theorems. So consider the symmetry group S sub 3. It's order 3 factorial. It's order 6. Here it is in terms of permutations. This is a kind of notation you used in senior level algebra probably. Here's a group table for it. It's the symmetries of a triangle. S sub 3 is it equals S sub 3 equals a dihedral group. The symmetries of a triangle, by the way. That's why rows for rotations and mu's for mirror images. But anyhow, it's a group of order 6. Let's find the Celo2 subgroups. Okay. I like mentioning dihedral groups because it gives me something to visualize. You've got Celo2 subgroups. So this would have to be the identity and an element that's its own inverse. Well, all these mu's, the mu's are their own inverse, as you can see along this part of the diagonal. Yeah, they represent little mirror images. So you apply that twice and you get an identity. These are the only Celo2 subgroups, 2 is prime, of this group of order 6. With P equals 2, we see there's 3 subgroups of order 2. 3 is congruent to 1 mod 2, as we expected. Third Celo theorem told you how many you would find. First Celo theorem told you you'd find such subgroups. I can't quite talk about normality, I guess, in this. Pick such small subgroups. If we look at conjugation and we conjugate these 3 subgroups, we should get other of these 3 subgroups. These are Celo2 subgroups. If you conjugate them, you should get other Celo2 subgroups. If we conjugate them by elements of themselves, of course, you just get the thing back. If we conjugate this subgroup, say by row 2, this is the one that contains mu1, it gives the one that contains mu3. Conjugate the one containing mu1 by row 1, apparently it gives you the one containing mu2. Conjugate the one containing mu2 by row 1, and it gives you the one containing mu3. So it permutes these things around in a sense. And that's what the second Celo theorem told you. Conjugates of Celo2 subgroups or other Celo2 subgroups. We can use the Celo theorems, and we will use them in the next section, to classify certain finite order groups. The real application is showing groups are not simple. The second Celo theorem can be used to deal with showing that groups are not simple by allowing us to show that Celo2 subgroups are normal subgroups. Was a simple group? Simple group has no proper non-trivial normal subgroups. So no normal subgroups except the identity in the whole group itself. That's what a simple group was. We had some conditions where these Celo2 subgroups were normal subgroups. So if we've got a Celo2 subgroup that is a normal subgroup, then you ain't got a simple group. So that's how the applications will go. An example from Fraley, and then another example either from Hungerford or just from somewhere out there. We claim no group is of order 15 is simple. Suppose you got a group of order 15, order of G equals 15. We'll show that G has a normal subgroup of order 5. First Cielo theorem says G has at least one subgroup of order 5. It's got a Celo2 subgroup, if you like. By the third Celo theorem, the number of such subgroups is congruent to 1 mod p. Sorry, 1 mod 5 in this case, p equals 5, and divides the order of the group. So we need something that's 1 mod 5 and divides 15. The only thing that's 1 mod 5 that divides 15 is 1. So the number of Celo2 subgroups must be exactly 1. You only got one subgroup of a particular order, then that subgroup is a normal subgroup. Actually, one of the corollaries stated that. Let's run a look at that corollary. 5.8.3, back upstairs a little bit. Oops, that's chapter 1. It's looking for. Let me get it pulled up. Here we go. Corollary. Can't find it. There we go. Corollary part 3 states if there's only one Celo2 subgroup, that subgroup is normal. Yeah, by the conjugation argument from part 2. So we're applying that. If we show only one Celo2 subgroup, we must have a normal subgroup. In this case, yeah, no, there's a subgroup of order 5. It's a Celo2 subgroup, and it's the only one by the counting argument from the third Celo theorem. So that little corollary tells you must be normal. So any group of order 15 has a normal subgroup of order 5. So it's not a simple group. Simple groups have no proper non-trivial normal subgroups. So this group of order 15 can't be simple. Same idea, some bigger numbers. Every group G of order 483 is not simple. 483 factors as 3 times 7 times 23. By the first Celo theorem, this group G has a Celo23 subgroup. By the third Celo theorem, the number of Celo23 subgroups is 1 mod 23, and it divides the order of the group. The divisors of 483, the divisors of the order of the group, which are not multiples of 23, are 1, 3, 7, and 21. And a bunch of multiples of 23. But multiples of 23 are not 1 mod 23. They're 0 mod 23. So 1, 3, 7, and 21 are the only possible candidates for the number of Celo23 subgroups. And none of these are 1 mod 23. The only one that is 1 itself. So again, there must be a unique Celo23 subgroup, only one Celo23 subgroup. That corollary tells us that's a normal subgroup. You got a normal subgroup, then you don't have a simple group. So there's a couple ways we can show we're not dealing with simple groups, and easy little applications if the numbers work out properly in terms of showing the existence of normal subgroups. And that takes care of the Celo theorems. Next section, we'll look at classifying finite groups up to about order, I think it's order 15. And we'll use the equipment, among other things, of the Celo theorems to narrow down how many groups could exist of certain orders. I will see you in section 2.6 next episode. Have a nice day.